The expectation maximization algorithm, or the EM algorithm as it's known, is actually a class of algorithms, which it's more of an approach to deriving an algorithm for approximately obtaining maximum likelihood or maximum a posteriori estimates of parameters when some of the data is missing. Some data is missing. So one example of this is in the hidden Markov model. In the hidden Markov model, some of the variables, notably, the x's, this is the hidden Markov model, and the hidden variables are not observed. Or rather the z's. The x's are observed, but the z's are not. And so that is one example of what we mean when we say some data is missing. Another example is in a mixture model. So the Gaussian mixture model that we're going to take a look at soon as an approach to clustering is another example in which the EM algorithm is applicable. And there are a huge number of other applications, because very, very often you have latent variables. These z's were latent variables. And very often in more interesting models, you have lots of latent variables floating around. And so the EM algorithm is one way to tackle that, the parameter estimation problem when you have missing data or latent variables. And you can always, when you're trying to choose, these are just sort of maximization problems, and there are always sort of off-the-shelf standard optimization routines for maximizing functions and stuff. But what's special about the EM algorithm is that it exploits the structure of particular kinds of problems. And in particular, what's special about this problem is that we're trying to maximize the likelihood or the posterior probability. And usually for an EM algorithm, you assume that it's the probability of all the data together. I mean, if you could observe all the hidden data as well, usually that comes from an exponential family, and that's when the EM algorithm is particularly applicable. So let's talk about what it is. What is the EM algorithm? I'm going to give you the sort of general formulation, the setup, and the general formulation for the EM algorithm. And in the next video after this, we'll talk about why this we'll give some motivation for why you might do this. Sort of a natural derivation of the algorithm. So we're given some data, some observed data, rather, and let's call that x. X is these observations, x1 through xn. But our model is x and z. We have random variables x and z, which are distributed according to they have some joint distribution, p theta, for some unknown parameter theta in some set of parameters. And typically this p theta here is an exponential family. That's what I meant when I said that the joint of all of them together is typically an exponential family. That's when the EM algorithm really shines. Okay, and then this x we're modeling here, this x is a vector x1 to xn, which is modeling the data here. And z is just some other random variable. That's going to be the latent random variable. Our goal then is let's first talk about the MLE. So if we're going to focus on the MLE first, and then later we'll talk about how to modify this to get map estimates. So we want to get some MLE, and of course an MLE is just a maximizer over the theta of the probability of the data. But now here it's just the probability of x. It's the probability of our observations, because we don't get to see the z's, so we can't maximize the probability of x and z. So we're maximizing the marginal probability of x. And the issue We've done MLE before, and what makes this sort of so different? Well, here's the issue. The issue is that, as I was just saying, this is a marginal distribution. So it's this sum, if you write it in terms of the joint, it's this sum over z's. And this is difficult to optimize, to maximize. Oftentimes it's very difficult to maximize. And the reason is because of this sum. This sum makes it so that this resulting thing can be multimodal. Oftentimes it has, multiple maxima, many maxima. And oftentimes, because of the resulting, if you try to differentiate this with respect to theta or some of the parameters in theta and set it equal to 0, you'll get some implicit equation that it has to solve, but it's difficult or impossible to solve it analytically. So that's the problem. So what's the solution? The solution, according to EM, there are other solutions, but the EM algorithm addresses this by iteratively improving your estimate of this parameter theta in the following way. So you first initialize theta to some theta, so you choose some theta naught, some theta 0. And then for t equals 0, 1, 2, etc., we'll do the following two steps. First is the so-called E step. And in the E step, you compute the following quantity. And usually you don't have to, this is a function of theta, but usually you can get something to represent this function. You can get the necessary sort of components of this function to describe it without actually, computing it for every possible theta. So let me just make it sort of vague for now, and we'll look at specific examples in the future. So this function q of theta and theta t is the expected value under the parameter theta t of the log of the probability under the parameter theta of the joint distribution x and z, given that x equals the observed value little x. So x was our observed up here. This was our observation. So this is a conditional expectation of the log of the joint distribution under theta. Okay, that's the E step. And the M step, the so-called M step, is you choose theta t plus 1 to be a maximizer, to be a argmax over thetas of this Q function. Maximizing Q theta with theta t. And then you iterate. So you alternate between the E steps and the M steps. So this is for t until convergence, or some maximum number of iterations. And oftentimes, well, especially when you choose an exponential family for this joint distribution, this maximization can be done analytically, and there's a unique maximizer. And also, when you use exponential families, typically, which is typically the case, you can get an expression for this expected value as a function of theta without explicitly solving it for each theta. Okay, so I'm going to motivate this. This may be a little sort of, where does this thing come from? What is this crazy conditional expectation, and what's the log doing in here? I mean, this just seems totally, out of the blue. So in the next video, I'm going to uh, we're going to arrive at the same, essentially the same, algorithm as this, but starting from a very natural perspective, trying to just maximize the likelihood. This was the thing we were originally trying to do here. We wanted to maximize this, right? And so, how does this procedure maximize this marginal likelihood, this marginal, the probability here? So we're going to see in the next video why that's the case, why you arrive at this when you try to maximize this. And let me briefly mention here some pros and cons. Pros, some advantages of the EM algorithm. One is that you're guaranteed that the probability of x under theta t plus 1 is greater or equal to the probability under theta t when, this is the sequence of thetas obtained under this EM algorithm. So you're guaranteed that at least you're not decreasing the probability, so that's good. At least you're not making things worse, right? And oftentimes, it does, significantly improve your likelihood. Oftentimes works very well. And, well, I guess that's my second comment, is that it works well in practice. EM tends to work well in practice. And briefly, a couple cons. Not guaranteed to give a maximum likelihood estimate. And part of the reason is because there could be multiple modes here, and you might get stuck at a local optimum and not be getting to the global optimum. So it's not guaranteed to give a maximizer. Another thing which is always true for maximum likelihood is that maximum likelihood can overfit, may overfit, but the solution is you can use maximum a posteriori with the EM algorithm also, and we'll see how to do that. Another couple things I'll just mention here. Convergence can be slow. The EM algorithm sometimes can take a while to converge, but there are sort of variations on EM. There are a huge number of variations and sort of extensions to the EM algorithm, and some of these address the speed of convergence. And one final sort of con I'll mention here is that the EM algorithm is in some sense specialized to exponential families. And it may be that, so I mentioned here that this maximization can be done oftentimes analytically when you have an exponential family, when this joint distribution is an exponential family. But if it's not an exponential family, of course you can still apply the EM algorithm, but it may be that you can't compute one of these two steps analytically. You may not be able to compute this conditional expectation analytically, and you may not be able to compute this maximization analytically. So there are, of course, extensions where you can do approximations and all sorts of things like that. So that's the EM algorithm, and I think it's probably clear why this is called the E step, because it's an expectation here, and this is the M step because it's a maximization. Sometimes some expositions of this make it confusing as to why this is called the E step and why this is called the M step. Okay, so that's EM, and next we'll take a look at a little more motivation for why you might, how you might arrive at this algorithm in a sort of natural way.